Okay, so this is lecture 4, part 3, continuation of our discussion of applications of derivatives. And in this section, it corresponds roughly to section 4.3 of your text, and we're going to be talking about how derivatives affect the shapes of graphs. So many applications of calculus depend on our ability to deduce facts from a function f and information concerning its derivatives. So we've already seen this particular with the parabola. We like to know the vertex of a parabola because it answers whether some quantity is maximized or minimized. So we've seen this all since algebra pretty much. So how derivatives affect the shape of a graph. All right, so the derivative of f represents the slope of the curve of f at the point x, f of x, okay? It tells us the direction in which the curve proceeds at each point. So it's reasonable to expect that information about the derivative will provide us information about f of x, which it certainly does, and we've emphasized this quite a bit, okay? So, you've got some function, and we know that, for instance, if a function is, say, shaped like this, okay, some sort of serpentine shape, and we know that on this interval, the function is increasing, and that's due to the fact that the slopes of the tangent lines to each point on the function have positive slopes. Okay, so increasing functions are related to tangent lines with positive slopes. And then we come along to this transition point where the slope of the tangent line is 0, and basically the tangent line is horizontal, and the function is neither decreasing nor increasing at this point. It's a point of transition. And then once we get to the right, say, of this particular point, we notice that the function is decreasing, and the slopes of the tangential lines are negative on this interval. So the function is a decreasing function, and that correlates to a tangential lines with negative slopes. Okay? So that's pretty much, if you can keep this in mind, keep this straight, then you should have no problem here. Okay, so what does f prime say about f? All right, so as we just said, from a to b, we have an increasing function. The slopes of the tangential lines are positive. At b, it's a transition point from an increasing to a decreasing function, and the slope of the tangent line at b, at x equals b, is 0. From b to c, we have a decreasing function, so the slopes of the tangential lines from b to c are less than 0. At c, we have a transition point from decreasing to increasing function, and the slope of the tangent line at x equals c, of course, is 0. And then from c to d, we transition back to an increasing function where the slopes of the tangential lines are positive. Okay, so how many times have we said that? Probably more than we care to do so. Okay, so et cetera, say between b and c, and so forth. So take a good look at this. All right, so f increases when f prime of x is positive and decreases when f prime x is negative. And so to prove this, as always the case, we can use the mean value theorem. Okay, so the mean value theorem is used to establish beyond a reasonable doubt what the derivative says about a function. Okay, so we have what's called the increasing decreasing test, the ID test. I often call it the idiot test, okay, increasing decreasing test. So two parts. If the derivative is greater than 0 on an interval, then f is increasing on that interval. If the derivative is less than 0 on an interval, then the function f is decreasing on that interval. All right, so the ID test, increasing decreasing test. So the proof of part A. Let x1, x2 be any two numbers in the interval, with x1 being less than x2. And according to the definition of an increasing function, we have to show that f of x1 is less than f of x2 for any x1, x2 in an interval. Okay? That is for any x1, x2. Not just a pair, but all of them. For any x1 less than x2. You pick two numbers in an interval, and this criteria holds. All right. We're given that the derivative is greater than 0, and we know that the function is differentiable on the closed interval. So that's a lot of information already. So by the mean value theorem, there's a number c between x1 and x2 such that we have this linear relationship. fx2 minus fx1 is equal to f prime of c times x2 minus x1. So this is the mean value theorem. Now you see its utility. Okay, this is the key point right here. So, and remember, c is between x1 and x2. Okay, now f prime of c is greater than 0 by assumption. Okay, the part A, and x2 minus x1 is greater than 0 because we established that x1 is less than x2. We're given that. We asserted that. So the right side of the equation. All right, so since x2 is greater than x1, and we know that the derivative is greater than 0, okay, on the interval x1 to x2, okay, that has to be greater than 0. All right, and that holds for any x1, x2. All right, and so that means that fx2 minus fx1 is greater than 0. Okay, mean value theorem, a tremendously powerful theorem. And it has other applications as well. Okay, so we have fx2 minus fx1 is greater than 0, or fx1 is less than fx2. And this shows that f is increasing. Now, part B, for the decreasing part of the proof of the ID test, done similarly. Okay, it's done similarly. And what else? Okay, so we want to find where, say, this function, this polynomial function, is increasing and where it's decreasing, on which intervals, okay? So how can we do that? Well, okay, so we take its derivative. Here's its derivative. We factor it, okay? And to use the ID test, we have to know where f prime of x is greater than 0 and where f prime of x is less than 0. It depends on the signs of the three factors. So guess what, folks? We're back to using our table of signs again. So namely, we can use our table of signs. I think this, okay, so we have three factors, right? So there are three factors: 12x, x minus 2, and x plus 1. So that's slide 14. Okay, so here are our table of signs. So we had 12x, x minus 2, and x plus 1. Okay, and then we have f prime of x. So remember the table of signs. Okay. Okay, and so it's a polynomial, so the domain is for the derivative would be the set of the entire x-axis, and so we have zeros of the factors at -1, 0, and 2. All right, and so we just established the signage for the function. Okay, so if x is less than 0, this factor, of course, is negative. If x is less than 2, this factor, of course, is negative. And if x is less than -1, this factor, of course, is negative. Okay, and so the derivative is negative from -infinity to -1, positive from -1 to 0, negative from 0 to 2, and positive from 2 forward. So we would expect then that the function is decreasing from -infinity to -1, increasing from -1 to 0, decreasing from 0 to 2, and increasing from 2 forward. So kind of a potential sketch of the graph then would be, okay, so here's -1. So what does decreasing look like? Decreasing looks like this, right? And then from -1 to 0, we're increasing. And then from 0 to 2, we're decreasing. And then 2 forward. So it's going to be something like that, kind of a W shape. Of course, it won't have sharp corners because it's a polynomial. So let's see here. Let's see how Stuart rambles on here. So slide 14. Slide 15. Yep. And so lo and behold, here's their rendition of the table of signs, which is a little more complicated than ours, but nevertheless they come to the same conclusions as we just developed on the previous screen. Okay, so you can interpret the information. They kind of rotated, they pivoted our table of signs, so without the pivot. Okay, all right. So so we know that. We know this. So we know this now. We know this now. Okay. All right. And so here's the graph of the function, of course. So clearly, we already came to the conclusion that the function is decreasing from 0 to -2, increasing from -2 to 0, decreasing from 0 to, what was that, 0 to 2? Yeah, decreasing from 0 to 2. Slide 16. All right. 18. Yeah, decreasing from 0 to 2. Here's 2 right here. Okay, that's funny how that detaches. Okay, decreasing from 0 to 2, and then from 2 onwards it increases. Okay, so can I copy? So let's match that against what we had here. Yeah, so match. So you see, here's truth right here, and then here's what we anticipated. Very similar to what we anticipated. All right. Okay. All right. So let's see what's next. Slide 19 now. Okay, so slide 19. Okay, so from section 4.1, if f has a local maximum or minimum at x equals c, then c must be a critical number, and that's from Fermat's theorem. Okay, however, not every critical number gives rise to a maximum or minimum. Okay, so we need a test that tells us whether or not f has a local max or min at a critical number. All right, fair enough. So this moving along. So you can see from the figure that f of 0, which equals to 5, is a local max value because f increases from -1 to 0 and decreases from 0 to 2. In other words, at x equals 0, we have this point of transition from increasing to decreasing function. So f prime, okay, so in terms of the derivatives, the derivative is greater than 0 from -1 to 0, and it's less than 0 from 0 to 2. Okay, so we should be ringing in our heads now. All right, so in other words, the sign of f prime of x changes from positive to negative at 0. Okay, and so now we have what's called the first derivative test. Suppose that c is a critical number of a continuous function f. If the derivative of f changes from positive to negative at c, then f has a local maximum at c. Okay, there's your first derivative test. And then we can make the same characterization for a local minimum. If f prime changes from negative to positive at c, then f has a local minimum at c. Okay, and I think we've talked a lot about this so far this semester. Okay. If f prime does not change sign at c, even though c is a critical number, if f prime is positive on both sides of c or negative on both sides of c, then f has no local maximum nor minimum at x equals c. So for instance, this could be an example of, say, a branch of a tangent function, or this could be a branch of the cotangent function. And see, we have this transition. There's no transition occurring at the critical number, but there is a concavity change. So typically, these will be called inflection points. Okay. So the first derivative test is a consequence of the increasing-decreasing test. Let's see, so for instance, in this figure, the sign of f prime of x changes from positive to negative at c. F is increasing to the left of c and decreasing to the right of c. So it follows that f has a local max. Okay, so yeah, so this is the increasing-decreasing test analysis. All right. So here's, you can remember these diagrams for max, min, and nothing, right? Nothing going on. Okay, so the four diagrams that can help us visualize the first derivative test for any function. Okay. All right, so example, find the local minimum and maximum values of f in example 1. Okay, so did they do that? Okay, yeah. So, all right, so let's go back. So I'm on slide 28. Okay, so let's go back here. So now, we can use our table of signs in conjunction with the first derivative test. Here, at x equals -1, okay, we transition from decreasing function to increasing function. So without knowing the sketch, we can say that the profile of the derivatives, decreasing, increasing, -1. All right, and so if we know that those 4 sketches, referential sketches, then this constitutes, x equals -1 constitutes a local minimum. At 0, okay, to the left of 0, we're going this way, change at 0, and then we start going down. Okay, so this is at 0. So 0, at x equals 0, we have a local maximum. And at 2, we do this thing. We do the same thing we did at -1. We were decreasing for a while at x equals 2, then we change directions and we start increasing. So 2. Okay? And it doesn't matter where in which quadrant, 1, 2, 3, or 4, where this happens. All that matters is whether we change from decreasing to increasing in the quadrant. Okay, doesn't matter where it happens as long as you have this this profile. Okay, so back to slide 28. All right. Slide 29. Okay, so we've discussed that. We discussed this. By the way, these slides are on the class website. Okay, 31. Okay, so now how about we consider this function? We want to find the local max and minimum values of the function g of x equals x plus 2 sine x on a closed interval 0 to 2x. Okay, so again, we'll calculate the derivative. G prime of x is equal to 1 plus 2 cosine of x. Find the critical numbers. So g prime of x is equal to 0 and cosine x is equal to -1/2. All right, so suppose you don't know where cosine x is equal to -1/2. Well, what we can do, okay, so we're on slide 32, we can do this. Let's see here. Perhaps we can go to my trigonometry website and hunt for something. Let's insert an internet browser. Okay. And let's go to my trigonometry website. And let's see if we can find a resource here. Okay. Let's see here. That looks okay, but can we do better? Let's see if I have. Let's keep going here. Oh wait, here we go. Trigonometric function. Let's check this link right here. And let's check reference angles. Okay, so let's see here. What would happen if I were to copy this figure? Let me copy the figure. Yeah, copy. Okay, and let's see here. Let's go to another slide. And let me paste this in here. Okay, so now the question was, on slide 32, we are trying to find where g prime of x is equal to -1/2. I believe that was it. let's see, 32 was it? So where g prime of x is equal to 0 and cosine x is equal to negative 1/2. So what values of cosine x equal to 1/2? All right, so we can come to this, okay, and let's see, we can say, okay, cosine x equals to 1/2. So that would be, well, that's still not very useful, is it? Okay, so let's go back here and see if we can find something else. How about, we have a graph of the trigonometric function, the trig function. Sine, arctangent, secant. Do I have a graph of the cosine anywhere? Arcsecant, arccosecant, I don't see cosine. See sine. Didn't include sine, cosine. Okay, so no luck there. Okay, so let's see. Let's go to the class calculator. Should have gone here first, shouldn't I? Okay, so we're hunting for where cosine x is equal to negative 1/2. So y is equal to cosine x. And in this problem, we were confined from 0 less than or equal to x less than or equal to 2 pi. So the f was at least, okay? But in this case, we're just interested in this, okay? So let's change our window properties to be in terms of this. No, not this. This x labels are in terms of pi. Dismiss the window, and let's zoom in. So here's the cosine function. I guess we should graph what x equals to, cosine x is equal to what, negative 1/2. Okay, so there's the line. Oh, so we'll probably have to do a periodic extension for our derivative. So let me go ahead and okay. Okay, so it'll be shown in blue. Now, let's just it will just do free range cosine. Okay, so is that the question? Slide 32, where cosine x is equal to, let's check it again. Cosine x is equal to, I'm sorry, not, I beg your pardon. Cosine x is, the output is equal to 1/2, not the input, sorry. Let me go back. That should be y is equal to, y is equal to negative 1/2. So y is equal to cosine x from 0 less than or equal to x less than or equal to 2 pi, and y is equal to negative 1/2. So we're interested in where the outputs are. Okay, so, and let's see, adjust our x-axis to be in terms of pi. Okay. No, wrong axis. I have the y-axis because it's hard to use this technology. The internet is so slow. Okay. Okay. Now, as soon as I get the focus back, okay. So now we can discern then. Here's the red curve, of course, is cosine x on 0 to 2 pi, and the blue line is y equals to negative 1/2. And so where they two intersect are the values of x where the cosine of the output is equal to negative 1/2. So we have that point right there. So, and we have this point right here. Okay. So let's capture this screen. Copy the image. All right, and so we'll go back to slide 32. Okay, so we want g prime of x equal to 0, so when cosine x equals to -1/2. All right, and they give you the solutions, but you need to know how. One way of finding the solutions, of course, would be to use this calculator, and that's deduced from this picture right here. Okay, and ideally, if you're really proficient in trigonometry, you shouldn't have to do all of this work. You probably have this understood and perhaps even memorized. Okay, so in case you don't have your trigonometry down, or if you've forgotten, here's the technique that you would use to answer that particular question. All right, so let's move this off. Okay, all right, so back on task. All right, next slide, slide 33. So g is differentiable everywhere, and the only critical numbers are at 2 pi3 and 4 pi3. So they create another table of signs, and so we know from 0 to 2 pi. Okay, so in this case, the graph we drew might be useful because it may be a little more, although you can create a table of signs. For functions that aren't polynomials, or rational functions, it's a little more challenging. But nevertheless, we can see that this is the graph of g prime of x right here. Okay, this is g prime of x. And we can see that from 0 to 2 pi over 3, it doesn't look right, does it? Oh, okay, this is cosine. Oh, okay. Okay. Oh, g prime of x. So we need a graph for g prime of x. So let's do that. G prime of x is equal to 1 plus 2 cosine of x. Okay, all right. Yeah, so this only established the fact where cosine x is equal to half. So actually we need to look at the graph of 1 plus 2 cosine of x. Okay, so we know that, all right, yeah, so we can just use this table. So we know that if x is less than 2 pi3, and we're on the interval 0 to 2 pi, okay? So if x is less than 2 pi3, then cosine function would range between 1, as shown in this graph, to -1/2, okay? And all numbers between -1/2 and 1. So whenever you plug a number between -1/2 and 1 into this function right here, the output will be positive. So g prime of x will be positive on this interval. Now when we go from say -1/2 to, I'm sorry, from 2 pi3 to 4 pi over thirds, you'll see that the cosine function takes on values between -1/2 and -1. Okay, you see that? You can see it by this graph right here, between -1/2 and -1. And so when you add any number between -1/2 and -1 to g prime of x will be negative. So g prime of x is decreasing on the interval. They left off a pi right here. That should be 2/3 pi to 4 pi over 3. And then from 4 pi over 3 to 2 pi, of course, we can see that the cosine function takes on values from -1/2 to 1. Okay, and so when you take any number on that interval and plug it into this function g prime of x, the output of g prime of x will be positive, and so it's increasing. So we can deduce then that x equals 2 pi over 3 will be a local maximum, and at x equals 4 pi over 3, you transition from decreasing to increasing, so 4 pi over 3 will be a local minimum. Okay, so we can anticipate that's what the next slide will say. Okay, so as g prime so let's read this. As g prime changes from positive to negative at 2 pi over 3, the first order tells us there's a local max and the local maximum value. Okay, so here they calculate the coordinates of the local maximum value. And so it's found by taking 2 pi over 3 and plugging it into g. Okay, not g prime, but g. And so that would be x plus 2 sine x. And so that turns out to be 3.83. Okay. All right. would have been nice to have this on the first project, wouldn't it? Okay, and then the local min, okay, we deduced that that occurred at x equals 4 pi over 3, and so g at 4 pi over 3 is 2.46, so that's a local minimum for the function. And here it is the sketch. There's the sketch. And of course you could verify that more accurately using the class calculator. Okay, so max min. Okay. All right, so here's a figure that shows two increasing functions on an open interval a to b. All right, yeah? How can we distinguish between these two types, okay, of behavior? So both graphs join point A to point B, but they look different because they bend in different directions. Yeah, so yeah, so in frame 1, you see an example of a concave up situation, and in frame 2, picture B, that is, you see an example of a function that's concave down. Okay, so how do you distinguish between these two types of behaviors? Okay. All right, so okay, so here we draw the tangents. So just draw the tangents. And if the tangent lines, as shown in figure A, cradle the function, if they cradle the function like you know, you're holding something in your arms, okay, then we have the concave upward concept. Now, if the tangent lines cover up the function, okay, on an interval, then it's concave down. You see how the tangent lines cover up the function? The function is blocked by the tangential lines. Okay, and here the function rests on top of the tangential lines. Okay, so that's the distinction. Okay, and what else? Slide 40, slide 41, slide 42. Okay, so if a graph of f lies above all of its tangents on an interval I, it is called concave up. If the graph of f lies below all of its tangents on an interval I, it's called concave down. Okay. All right, so there's your concavity, and the figure shows the graph of a function that's concave upward on intervals b, c. So from b to c, yeah, see, the function is cradled by all of its tangential lines. It sits above them like that. And d to e, okay, x equals d is an example of a vertical tangent. But see how it's cradled? Okay, and e to p, where's e to p? Okay, it just sits right on top of those tangential lines, like so. And it's concave downward on where? A to b. Okay, you see how the function is blocked, held in check from rising upward by the tangential lines. So from A to B, it's concave down. From C to D, you see how it's, try drawing the tangent lines below it, and that won't happen because you can see the direction of the tangent lines are like this and then like this, okay? And let's see, here we, from P to Q, okay. All right, so it's basically, it spills water on the interval. You can't pour water in and it'll hold water. So from E to P, you dump water in here, and it, you know, it kind of will hold water if it had a little more like this. Here it'll hold water, here it'll hold water. So if it holds water, it's concave up. If it spills water, it's concave down. That's maybe another analogy for discerning the two concepts. Okay, what else? So how does the second derivative determine the intervals of concavity? So now we have a second derivative comes into play. Okay. All right, so from this figure, you can see that going from left to right, the slope of the tangent increases. Yeah, so going left to right, the slopes of the tangents are increasing. This means that the derivative, f prime, is an increasing function, and therefore its derivative, f double prime, is positive. Okay, so in other words, all you're saying here is that if f double prime is greater than 0, okay, that means the tangent lines are increasing. The tangent function, f prime, is an increasing function. F prime is an increasing function if its second derivative, if that is, if the tangents to the f prime are greater than 0. Okay, so if this is true, then we are concave up on an interval, right? And you have to draw a graph that looks like that. Okay, all right. So we can anticipate that the next frame will probably talk about concave down. Yeah. So in this figure, the slope of the tangent decreases from left to right. So f prime decreases, and therefore f double prime is negative. All right, so what do we have? So we have f prime is a decreasing function, and whenever you have a decreasing function, the slopes of its tangent lines are negative. Okay, and in this profile, the function is concave down. So when the second derivative is less than 0 on an interval, the function is concave down and has to be drawn that way, and no other shape will work. Okay, no other shape will work. No exceptions. Okay, so theorem. If the second derivative is greater than 0 for all x in the interval, then the graph is concave up on that interval. If the second derivative is less than 0 for all x in the interval, then the graph of f is concave down on that interval. All right, so and here's an example of a population graph for some honeybees raised in an apiary. I guess that's a beehive. All right, so how does the rate of population increase change over time? When is the rate the highest, and over what intervals is p concave up or down? Okay, so let's see. Let's copy this figure, and we'll go on to the next slide and keep it in perspective as we transition. Okay, so by looking at the slope of the curve as t increases, so as t increases, we can see that the slopes of the tangential lines change very slowly. Okay, so the numbers don't differ by that much. It's just the slopes are essentially a small number. But the slopes get larger until it reaches a maximum at t equals 12. All right, so the slopes of the tangent lines get larger and larger until t equals 12 weeks. And then after 12 weeks, we see that kind of sort of that the transition, the slopes of the tangent lines begin to level off. Okay. All right. So the slopes of the tangent lines start to level off at t equals 12. So as the population approaches its maximum value of about 75,000, so the maximum value is here, right? So I guess he calls that 75,000. And that's called the carrying capacity. The rate of increase, which is a change in population with respect to time, approaches 0. Yeah, so the rate of increase, so we become horizontal. The slope of the tangent line becomes horizontal. And so the curve appears to be concave upward on 0 to 12 and concave downward on 12 to 18. Okay, and that appears to be. Okay, so yeah, hopefully we see that. Okay. So we changed concavity roughly at t equals 12 and population equals 38,000. And of course, the point at which you change concavity is called the inflection point. So here is your approximate location of your inflection point right there. All right. Yeah, so what the inflection point tells us is that, okay, is that the rate of population increase has its maximum there, okay? So the rate increases, okay, in other words, the rate of population increase, the change, okay, so the rate, okay, so what is the rate of population increase? Well, population increase, this term right here, is your change in population with respect to time, okay? Just remember from chapter 3, Okay, now the rate of population increase is the change of the population increase with respect to time. Okay, remember the related rate section? Okay, and so so this second derivative of the population with respect to t ceases to become greater than 0 at the inflection point. Okay, right at t equals 12, the second derivative p changes from positive to negative. Okay, and that's at that point. That's where the change in p with respect to t, the slope of the population, the slope of the tangent line to the population curve achieved its maximal value, and then all of a sudden it just crashed. It started going negative on us. Okay, all right. So that's what happened. So the inflection point is the point where the curve changes its direction of concavity. Okay. Okay. So a point P on a curve is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward, or from concave downward to concave upward at P. That's your inflection point. And we've done this, right? I think we've seen this figure. We've already analyzed this figure. And in view of the concavity test, okay, so the concavity test, there's a point of inflection at any point where the second derivative changes sign. Okay, so that's called the concavity test. It's where the direction of the derivative, second derivative changes sign. Okay, the point at which the second derivative changes sign, we'll call that the concavity test. Oh, here's an interesting question. All right. Sketch a possible graph of a function f that satisfies the following conditions. All right, so let's give this a go. So what I'll do is I'll do it on a different slide. Let me copy and paste that. So we want to sketch the graph of this function. So let me input another slide. All right, so we require that the first derivative be greater than 0 from negative infinity to 1. All right, so first of all, we'll need our coordinate axes. So it's no use trying to use a graphing calculator for this, okay, because we don't know what f is. But we can sketch its graph. Okay, so here are our coordinate axes. And the first derivative, so here's 1. Here's x, of course. Okay, and let's see, so the first derivative from negative infinity to 1 is greater than 0. So that means the slopes of the tangential lines to the graph it has to be an increasing function from negative infinity to 1. So here's a potential solution. We can do this, or we can have something like this, of course. Okay, but nevertheless, as long as you depict the slopes of the tangential lines being greater than 0 from negative infinity to 1, doesn't really matter where you draw it. The other constraints will tell you which quadrant to draw that branch of the curve in. Okay, this is called a branch. All right, so let's see here, and then from 1 to infinity, the first derivative is less than 0, so that means it has to be going something like this. Okay. Okay. All right. So now, okay. So the second derivative. All right. The second derivative is greater than 0 from negative infinity to negative 2. All right. So here's negative 2, and we require that the function be concave up. Okay. So it has to be concave up. So that means for concave up, it's got to do something like this. Okay. So, all right, so it's got to be concave up, from negative infinity to -2, and from 2, here's 2, it's got to be concave up. So that means we need to have something like, we need to be concave up and decreasing. So that would have to be something like, so how do you draw something that's concave up and decreasing? So maybe something like this. Okay. Very slow change. Okay, so this is concave up and decreasing at 2. All right. And then the second derivative is less than 0 from -2 to 2. Okay, so that would have to be, yeah, something like this, perhaps. Okay. Oh, we can't have that. Yeah, because okay, so it has to be increasing, which it is, and then, so 1 would have to constitute x equals 1 has to constitute a local max. Yeah, so x equals 1 has to be a local max, increasing, decreasing, concave down. So that meets the criteria. All right, so x equals 1 has to be a local max. Concave down from -2 to 2. Okay, and it's increasing from -infinity to -1. All right, and then we need an inflection point at -2. Okay, and then of course the limit as x approaches -infinity, the output is -2. All right, so we need, here's -2, so that would mean we would need a horizontal asymptote this way. Okay, and the limit as x approaches infinity must equal to 0. Okay, so that means we would have to adjust our graph to be something like this. So we would have to go up, down to 2, and then like this. So it would have to be above the x-axis for x greater than 2, because we require this. We require it to be, the first derivative is less than 0. We require it to be concave up. It has to be asymptotic with the positive x-axis. 1 has to be a local max. So the graph we anticipate would have to look something like this. Okay, so that seems to fit all of the pieces. Now we don't know the coordinates of the local max, but we know the local max probably has to be above the x-axis. Okay, so we anticipate our graph having to look something like this. All right, so let's check our answer. Slide 50, right? What was it? Slide. What was it? Somewhere down here. What was the problem? 56, was it? Okay, yeah, so slide 56 is the problem. All right, so let's see here. So the first condition tells us that f is increasing on this interval and decreasing, so that means that x equals 1 is a local max. Okay, and the second condition says that f is concave upward on this interval, and concave downward on this interval. So between -2 and 2, it's got to be kind of like a parabola pointing down. And from the third condition, we know the graph has 2 horizontal asymptotes. Okay, yeah. So now we just need to put all that together, and yes, so there it is. So you can compare that with our previous sketch, and it's the same. All right. Okay, what next? What next? Okay, so we can use the Okay, we can use the second derivative to actually calculate maximum and minimum values of a function. And it's a consequence of the concavity test. So second derivative test may have applications at time. So let's see what that's all about. The second derivative test. Okay, so suppose the second derivative is continuous near a number x equals c. So if the first derivative is 0, okay, the first derivative at x equals c is 0, and the second derivative is greater than 0, then f has to have a local minimum at x equals c. And that makes sense, right? It makes sense because think about what happens at a local minimum. Okay, local min, you got to be concave up. Okay, and in order to be concave up, you got to have the second derivative greater than 0. So that makes sense. So this is a good check. If you're not sure if you've identified a local min or local max, just use this test to check your answer. And of course, if you at a local max, the first derivative is greater than 0, and the second derivative is less than 0. Okay, so that makes sense. And that's your second derivative test. Find the critical numbers, and then check the sign of the second derivative. Now, of course, I think if the second derivative is equal to 0, then you can't conclude anything. Okay, so as long as the second derivative is not 0, it has utility. All right, so yeah, here you go, what we just talked about. Okay, so take a second to take in the slide. Next slide will probably, okay, let's see, what about this slide? Yeah, okay. All right, so let's see, x to the fourth minus 4x cubed. I think we sketched this on the first day of class. And we want to discuss this curve with respect to concavity, points of inflection, local mins, and local maxes. And then we want to draw the picture, without a graphing tool. Okay, what fun. So f of x is equal to this. Then the first derivative, of course, is 4x cubed minus 12x squared, which is equal to 4x squared times x minus 3. And the second derivative is here. Okay, so there you have the calculations. All right. And then, so to find the critical number, set the first derivative equal to 0. They occur at x equals 0, x equals 3. The second derivative test, we evaluate the second derivative at the critical numbers, so f double prime is 0. So we can make no conclusion as to whether x equals 0 is a local min or a local max. But in this case, f double prime of 3 is 36, and that's greater than 0. So at x equals 3, we have a local minimum. X equals 3 is a local minimum. X equals 0, we don't know. Okay, we need further investigation. Probably the first derivative test. So here we go. F of 3 is negative 27 is a local min. And the second derivative gives us no information. So now, can we sketch it? We can probably sketch it now. Okay, and so here they're using the first derivative to show that x does not have a local min nor max at 0. Now, okay, now students often make the mistake of saying, well, if the second derivative is 0, is that not an inflection point? No, that is not the case. If the second derivative happens to be 0 at a particular value of x, it's not necessarily an inflection point. But if it is an inflection point, if there is an inflection point, the second derivative of the inflection point, of the abscissa of the inflection point, the second derivative of the abscissa of an inflection point will be 0, but not vice versa. If the second derivative is equal to 0 at a point, then that's not necessarily an inflection point. Okay. All right. So so here they're analyzing concavity. We have a change in concavity at 0. Yeah, you have to use your table of signs to analyze whether x equals 0 is an inflection point. And in this case, using the table of signs, from negative infinity to 0, this function is positive. From 0 to 2, the function is negative, and then from 2 to infinity. So clearly, there's a change in concavity at x equals 0, and there's a change in concavity at x equals 2. So in this case, x equals 2, or rather x equals 0 is an inflection point, and x equals 2 has to be an inflection point. Okay, because that's where the table of signs says where it changes concavity. So this is just essentially a table of signs of the second derivative. and we look for changes in the signage of the second derivative. All right. 0, 0 is an inflection point, and I would suspect that 2, -16 is an inflection point as well. All right. So that's how you find inflection points. So inflection points are found from the table of signs, not by setting the second derivative equal to 0. Okay. All right, so here's the sketch. So 0 is an inflection point, 2 is an inflection point, x equals 2 is an inflection point. There's your local min, and we didn't have any local maxes on this graph. Okay, so just like, and this is how we started off the class. All right, so let's see here. Second derivative test is inconclusive when the second derivative is equal to 0. And at the second derivative equals to 0, there might be a max, a min, or neither. Okay, so what else? Okay, and it also fails when the second derivative doesn't exist. And in this case, you have to resort to the first derivative test. Yeah, and so forth. Okay. All right, so how about we sketch the graph of this function, x to the 2/3 times 6 minus x to the 1/3. Okay, so now taking the derivative of this might be a little bit cumbersome, but of course you can always use the online calculator. So let's copy this. I think I have a online. All right, so let's take these functions, okay, and oops, I need the function itself, so what slide was on? 76. And I just lost my web page, didn't I? Okay. So let me pull that back. So we go to section 4.3, slide 72. Okay, so let's go back. So 73 past the notes, right? So we're working with this function right here. Okay, so x to the 2/3 times 6 minus x to the 1/3. And so I was trying to okay, so insert So let's see here. We're trying to calculate the derivative of, so yeah, here's a derivative calculator. So we want to calculate the first derivative of this function, x to the 2/3 times 6 minus x to the 1/3. So we can go to this derivative solver right here, okay, and we can calculate the first derivative. So we'll have x to the 2/3 times 6 minus x to the 1/3. Okay, so let's see if that'll give us a derivative. Which will match what they have. So they say 4 minus x times 6 minus x. So here it is right here. It's a little bit hard to read, but right here. So yeah, so that agrees with what they have. All right, so you can use this derivative solver to solve complex derivatives if you're in a hurry. And we can go ahead and just select the second derivative. Okay. And see what that looks like. Okay. And so yeah, so here's the second derivative right here, and that matches what they have. So so there's a tool. So if you're given really a challenging function to take the derivative, and you spend a lot of time calculating this derivative, you can use this derivative calculator solver if you know how to plug in the function into the entry box. Okay, so it's really a nice thing to have. All right, so let's go back. Slide 76. Okay, so now I showed you how you can get the derivatives using a derivative calculator. All right, so, and then as f prime of x equals 0 when x equals to 4, right? And f prime of x does not exist when x equals 0 or x equals 6. So you have three critical numbers at 0, 4, and 6 for this function, okay? And what else? To find the local extreme values, we use the first derivative test. Okay, so why don't we use the table of signs to calculate where the extreme values are for this function. So let's go back. Let's see, slide 77. Okay, let's go back here, and let's take let's take these, and we'll assemble a table of signs. Okay, so let's assemble a table of signs for the first derivatives. So we'll do it the old school way. So the factors are 4 minus x, x to the 1/3, and 6 minus x to the 2/3. So these are the three factors. All right. Okay, and we're trying to find where this function, we're trying to find out where the critical numbers are the local mins and local maxes of this function are. So we have f prime of x, and the zeros of the factors would be at x equals 0. Okay, but 0 is not in the domain of the first derivative. Okay, and then we have x equals 4, which is in the domain. Okay, and then we have x equals 6, which is not in the domain. So remember, we're looking for a transition from plus to minus of the derivative, first derivative, or minus to plus. Okay, so if x is less than 4, this factor is obviously negative. If x is greater than 4, that factor is positive. Okay, so if x is less than 0, that factor is negative. If x is greater than 0, that factor is positive. Okay, and 6 minus x to the 2/3 is always positive because you're taking the cubic root of a square, and a square is always positive. So that number is always positive. So therefore we have our conclusion from negative infinity to 0, first derivative positive. From 0 to 4, first derivative negative. From 4 to 6, first derivative positive. 6 and onward, first derivative positive. So we have a change. We have a change in sign of the first derivative from at x equals 0. Okay, so that means we're to the left of 0, we're increasing, and to the right of 0, we're decreasing. Okay, so x equals 0 has to be a local max. Okay, and this is the increasing decreasing test we're essentially using here. Okay, so at 4 we transition from decreasing to increasing, so x equals 4 will be a local min. Okay. Okay, so that's how you process that. And then you'll, of course, do the same thing, which we just did with this, to identify the inflection points. So you want to do that? Let's do that. So let's identify where the inflection points are for f of x. So we'll build a table of signs for f double prime of x so that we can hunt for inflection points. Okay, so so we have x to the 4/3, and then 6 minus x to the 5/3. And then we have f double prime of x. So we're hunting for our inflection points. Okay, so 0 is not in the domain, and 6 is not in the domain. Okay, so if this factor is always positive or 0, because we're taking the cubic root of a number raised to the 4th power, and this factor will be negative if what's inside of parentheses is negative, because we're taking the cubic root of a number raised to the 5th. Okay, and so f double prime is less than 0 for x less than 0. It's less than 0 for x greater than 0, but less than 6. And it's greater than 0 for x greater than 6. So the only inflection point occurs at 6. So the inflection point, which I'll call an IP, occurs at the point 6, f of 6. So we'll have an inflection point there. Okay. So, and then here we have 0, f of 0 is a local max. And then 4, f of 4 is a local min. Okay. Okay, so slide 77. All right. So what kinds of conclusions do we get? 78. All right, so we found that out. Okay, so second derivative. Okay, so just using the second derivative test. Okay, so clearly at x equals 4, the second derivative would be what? Let's go back to that slide. So the second derivative is here. So at 4, if we plug in 4, we'll see that the second derivative will be greater than 0. Okay, and it will be. So we'll have, let's see, at x equals 4. So at x equals 4, we have a local minimum. So we should expect, if at x equals 4 we have a local minimum, then what? We should expect the second derivative to be positive, but it's not positive at x equals 4. So we have a mistake here, perhaps. So let's check. 4 minus x, x is 1/3, so it's less than 4. It looks fine. Negative to positive. So x equals 4 should be a local min, so that means it should be concave up. But the sign of the second derivative is showing concave down. Interesting. So there's a mistake here. Well, let's read on. Okay, so this is the first derivative. So at x equals 4, positive. According to this, for x less than 4, it's increasing on 0 to 4. How can that be? How can it be increasing on 0 to 4 and decreasing from 4 to 6? So that's not the conclusion I came to. Let's go back. I came to the wrong conclusion. For x less than 4. Oh, I see. Okay, so if x is between 0 and 4, I see. I made a signage error. If x is between 0 and 4 and we plug it into this factor, it should be plus. Sorry, I messed that one up. It should be plus. And then if x is greater than 4, it should be minus. All right, so I had it reversed. So this should be plus. And it's always good to check. Okay, and this should be minus. So there's my table of signs there. So actually, so at x equals 0, it's neither a local min nor a local max now. Oh no, that changes everything now, doesn't it? So that means we need to fix this. So to the left of 0, it's negative. To the right of 0 is plus. So that means x equals 0 is a local min. So we need to change this to a local min. And that changes this. So, okay, that should be a minus sign. So at x equals 4, we go, yeah, okay, so that should be a local max. So I had those wrong. Okay, so now when we plug in 4, we should get a negative number. So everything's adjusted. So as you can see, the second derivative test can spot errors in your table of signs. Okay. Okay, so no need for this. Okay, 79. Okay. Okay, so we've done that. This is a table of signs we'll mark here. Okay, and here's the graph. Okay, so all right, so they obviously left off something in the sketch. So we now obviously, in order to complete the sketch, we need to create a table of signs for f itself. Okay, by itself, the first and second derivative tests won't tell you where the graph lies above the x-axis nor below the x-axis. So we have to complete that portion of the assessment here. Okay, so by itself, these pieces of information are not sufficient. So let me patch in the omission from this lecture. Here's the graph. And so what we really need to do is we need to build a table of signs for the function itself. So this function right here. So the factors are x to the 2/3 and 6 minus x to the 1/3. And okay. And so the zeros occur at x equals 0, x equals 6. Since it's a polynomial, well, the domain is the entire x-axis. We're not taking square roots of negative numbers or anything like that. Okay, so this factor is always positive. And then for x less than 6, that factor has to be positive, right? And for x greater than 6, it has to be negative. So f of x is positive for between negative infinity and 0, and that's shown here. And it's positive, it's above the x-axis between 0 and 6, and that's shown here as well. And then it's below the x-axis for x greater than 0, and as you can tell right there. So now let's see how we can leverage the other pieces of information. Now, we notice that at x equals 6, there's a change in the second derivative, the signage of the second derivative. So it changes from, the second derivative changes from concave down to the left of 6 to concave up to the right of 6. So this is an IP right here. And we also know that the output of the function is 0. So it's also, not only is it an inflection point at 6, 0, but it's also an x-intercept, right? It's an x-intercept. And we know that 0, 0 is an x-intercept. So what else? All right, so we know that at x equals 0 is a local minimum, which is shown here. And we know that the function is above the x-axis in the neighborhood of x equals 0 is shown here. Let's see what else. The function does not change in concavity at x equals 0, but the function is concave down and above the x-axis for x less than 6. Okay, so for x less than 6, we have to be concave down, and we have to be above the x-axis. And what else? Okay, and also for x less than 0, we have to have the slopes of the tangent lines being negative. Okay, so for x less than 0, from the table of signs of the first derivative, the slopes of the tangent lines have to be negative. And from 0 to 4, the slopes of the tangent lines have to be positive. Okay, and since there's a transition in the slopes of the tangent lines to the function at 4 from positive to negative by the first derivative test or the inverse increasing decreasing test, we know that x equals 4 has to be a local max. So 4, there's the output, and then we have to decrease. We have to be decreasing for between 4 and 6, we have to be decreasing. And then from 6 onward, we have to be decreasing as well. So that we need, that's an error right there. We have to be decreasing. So from 6 onward, we're decreasing, and we're concave down, like so. Okay. So you see how it all fits? Basically, these 3 tables of signs. If you just create the table of signs for the function, the second derivative, and the first derivative, you can pretty much have the entire graph sketched out. Okay, so yeah, so this shape that we have that's shown here is the only shape that meets the criteria of the first and second derivative tests, as well as the table of signs for the function. No other shape will fit this. This is a unique shape. Okay, and of course you can always check your answer by using the online graphing calculator. But do the online graphing calculator last, okay? Because in the test, you'll be expected to analyze information from the table of signs for the first and second derivatives as well as with the function. Okay, so it's no use trying to sketch a graph and expect to call it complete. All right, so slide 81. All right, slide 82. Okay, so use the first and second derivatives of e to the 1 over x together with asymptotes to sketch the graph. Okay, so we want to sketch the graph e to the 1 over x. So let's walk through that. All right, so let me do this on a different slide. Okay, so the objective here is to graph this function. Okay, so now we have a facility for graphing functions. We can use the Chapter 1 lecture notes as well as the horizontal and vertical asymptotes ideas, as well as the first and second derivatives now to sketch the graphs of functions. So, so it says use notions of asymptotes. So what happens, what about this? The limit as x approaches infinity of e to the 1 over x. Okay, well that's equal to, by the limit laws, we can bring the limit operator into the exponent because the exponential function is a continuous function. Okay, we can do this, and then we know from a previous theorem that this limit is 0. So this would equal to e to the 0, and so that's equal to 1. Okay, And how about the limit as x approaches negative infinity? So the limit as x approaches negative infinity of e to the 1 over x is equal to e, bring the limit operator into the exponent. And again, that's equal to e to the 0, which is equal to 1. Okay, so the line y equals 1 is an horizontal asymptote. Okay, so now how about, now obviously 0 is not in the domain of the function, so the limit as x approaches 0 from numbers bigger than 0 of e to the 1 over x. Okay, so that would equal to e to the limit as x approaches 0 plus of 1 over x, and so that would be, all right, so 1 over x is this, right? It's the hyperbola. All right, and what happens as you approach 0 from numbers bigger than 0? You shoot up toward infinity. So e to the infinity is infinity. All right, so now how about the limit as x approaches 0 from numbers less than 0 of e to the 1 over x? Well, that would equal to e to the limit as x approaches 0 minus of 1 over x. And so we approach 0 from this direction and we shoot toward minus infinity. So that would be e to the minus infinity, which is equal to 1 over e to the infinity, which is equal to 0. Okay, so we have that result. So that means we're going to have a something, so this function, so just using asymptotes alone, we're going to have something that looks like this, just using asymptotes alone. Okay, we're going to have a hole. Looks like this. Now, e to the 1 over x is always above the x-axis, okay? And then we'll have something like this, and then we need a horizontal asymptote at y equals 1. So here's y equals 1. And so it's got to be asymptotic like this, okay? So just for asymptotes alone and using limits, we have something like that. Now, we have to, of course, account for any potential local mins, local maxes, and inflection points. So now we have to calculate the first and second derivatives. So I think we can do this without having to use the derivative calculator. So f prime of x by the chain rule is equal to e to the 1 over x times negative 1 over x squared, okay, which is equal to minus e to the 1 over x squared. Okay, so if x is less than 0, so, well, wait a minute. This means that the function is always a decreasing function, right? Because the numerator, this term right here, is always greater than 0. This term is always greater than 0. So a negative of a positive number is negative. So that means that we have a case where f prime of x is always less than 0. So the function is always decreasing. So f of x is a constantly decreasing function. And that's validated, at least in the first quadrant. We see that it's always decreasing. So how about the second quadrant? So the only thing we need to hunt for now would be, say, inflection points. Where is it concave up and where is it concave down to complete the analysis? So we just take the derivative of the derivative, second derivative. We can use the quotient rule for differentiation. So that would be x squared, the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. So I'll have to simplify that in some fashion. So simplifying that, that would be, we can factor e to the 1 over x. We can factor out an x. Okay, and so that would be, let's see here, no wait, hang on a second. We have some cancellations, right? Let's see here. Let's see, right. I have a cancellation here, cancellation here. Okay, so this would be, pretty simple now. So if double prime of x is equal to e to the 1 over x times 1 plus e to the plus 2x, I'm sorry, plus 2x divided by x squared. Okay, so the table of signs for the second derivative. We need the table of signs to analyze points of concavity. So, so the points of concavity would be, so what are the factors we have? E to the 1 over x, 1 plus 2x, and x squared. Okay, and then f double prime of x okay, so we have the zeros being, okay, well, 0 is not in the domain of the second derivative, but negative 1/2 is. So we have negative 1/2. Okay, so we've got to do it like that. So this is always positive. This is always positive. And for x less than negative 1/2, it's negative. If x greater than negative 1/2, it's positive. So that means here the signage for the second derivative from negative infinity to negative 1/2, the second derivative is negative. From negative 1/2 to 0 and beyond, the second derivative is positive. So that means this function will be concave down. So let's write it out. So concave down from negative infinity up to negative 1/2. And then it'll be concave up from negative 1/2 to infinity. So x equals 1/2 is an inflection point. So we have negative 1/2 e to the 1 over negative 1/2, which is equal to e to the negative 2, is an inflection point. And we have no local mins nor local maxes. So now we can complete our sketch. All right, so all we do then is identify this as negative 1/2. And so we're concave down up to negative 1/2. Okay, so let me zoom in a little bit better. So we have a hole at 0 because of this limit right here. And so at negative 1/2, the output is what? E to the minus 2. Like so. And so we're concave down. And then we're concave up like this. And then we terminate at the hole. And then, of course, 1. There's your horizontal asymptote. So I need to make it asymptotic like so. And then we know that it's above the x-axis for x greater than 0. And it's concave down, so it's asymptotic. So there's your graph like that. So your graph has to look like this. Pretty funky looking graph. Okay, so we can check our answer. Slide 82. Okay, so we can do it. Slide 83. Okay, we've done that. Okay, there are the limits. Okay, change of limit index, slide 84. Slide 85. Okay, slide 86. Okay, so they use the chain rule to calculate the first derivative, which I pointed that out. Slide 87, what's going on here? Yeah, so they show that there's no critical number. Slide 88. Second derivative, I believe that's what we found. Yeah, they used the quotient rule for differentiation. I think I forgot to square this. Yeah. Slide 89. Okay, so they analyzed the concavity. They found that the inflection point happened at here, so that was the conclusion we had. Okay, slide 90. Yep, so there's the there are the limits, so we came to that conclusion. Slide 91. Okay, and so forth. Okay. Let's go to the end. So there's the sketch. And then they check their work with the graphing device, and we know how to do that. Okay, so that is it for, so let me go back to our work with this function. Was it here? No, not there. Let me see, which slide was it on? This one? Yeah, let me go back and correct the second derivative. See right here, I forgot to square the bottom. I was going too fast. Sorry guys. It doesn't, fortunately it doesn't change the output. So let me just for correctness sake, make that a 4. Go back in your notes and correct that. Make that a 4. So make that a 4. Make this a 4. And that's the only change because x to the 4th is always greater than 0. So carelessness on my part in calculating the second derivative. I forgot to square the bottom in applying the quotient rule. Okay, so that is it for section 4.3 of the text. There's a tremendous amount of information in that section, but I think it's doable. It's a detailed-oriented section, but so just be able to understand the rules, first and second derivative tests, and inflection points, and concavity, and whatnot, and you can solve a tremendous amount of problems. Okay, so that will be it for this lecture.